The broadcast is now starting. All attendees are in listen-only mode.
Okay, good morning, everybody, and this is Dr. Mansour, and today is Saturday, April 11, and welcome, everybody, and sorry last time I was not available, and I believe I was able to send an email the last minute after the system was, or the internet in my area was down for about a couple hours in the morning, so I sent an email related to the last meeting, which was April the 4th. So I missed that, and also I missed with the construction group also April 4th. So I will try to squeeze one more day. I will look to my schedule, and I will be glad to squeeze another day to replace or to substitute for the day that I have missed. Today is the 11th, Saturday, April the 11th, and I will go to hydraulics and hydrology since already I missed that, so I would like to go back to cover this, and after that we'll talk about materials. Materials is very lengthy topic, and it has a lot of subtopics to be discussed. So this way I put it in 2 days like this, and as I said that I'll do my best to find another day to substitute. So this morning I emailed you something, and I hope that all of you received it, which is 2 mini exams. One mini exam related to hydraulics and hydrology with some kind of problems, probably I believe a couple problems related to something else, maybe settlement, consolidation settlement, I believe, and also stability problem. So I try to do my best to give you a flavor of almost everything, with the concentration of the topic or the topics that listed per this schedule. I do my best to stick with the schedule as much as I can. Okay, I hope that everybody is healthy and everybody is doing his best to stay healthy, and you and your family and your neighbors and your community and your society and the whole country and the whole world. I hope that everybody will be fine after this crisis is over. If you look to the NCEES, and let me start with this, the blue book, as all of you know, the NCEES, the practice exam booklet. You get another nice and clean one here. Nice, okay. And as I said last time, they may come up with a new edition. Maybe this July. I will see if there is anything that will be coming out this July or not. If you look to the type of problems, started on 120 of the blue book, and I believe all of you have the blue book. If you don't have it, please let me know, and I'll be glad to send these problems with my notes. You will find that the hydraulics and hydrology for the AM started with the problem number 120. And if you jump to problem number 121, okay, and 122, and 123, and this is the continuation of 123, and 124, and 125, and finally 126. Those are the problems in the, this is a vertical, so this is geometrics. Those are the problems, so there are 3 here, 4, 5, 6, total of 7. So according to the NCEES, 7 problems for hydraulics and hydrology. And if you look to the exam specifications, I believe this is what you will find. So if you go to the NCEES, let me bring here the green tab. You will find that under hydraulics and hydrology, they have 7 problems. So the hydraulics and the hydrology, they are NCEES exam specifications. You will find these topics, and they are saying that approximate number of questions to be 7. And here are the topics related to the hydraulics and hydrology. So let us do our best here and look to these problems, and hopefully that we can cover as many as we can. And I hope that you get a chance to finish mini exam number 3, the one I sent it last time. This is mini exam number 4. I'll do my best to give you as many as I can. So mini exam number 3, and I'll be glad to send you, but I need everybody to work these problems in mini exam number 3. If you did not receive it, I will be glad to attach it again today when I send my notes today to you. So the hydraulics and the hydrology H&H topics and subtopics are based on many empirical formulas. And the empirical equations, they have some limitations, and we need to be aware of limitations and units. And for example, we will find an equation V today. The velocity is equal 1.486 over N RH 2/3 square root of S. This is one of the equations we are going to see today. So this equation, this is the famous Manning equation or Manning formula, and you will find that this is used only for US customer units. Because if you look to the same equation using the SI, the System International, the SI, you will find that 1.00 divided by N RH 2/3 square root of S. And we're going to see all these equations today, and we need to be familiar with them. Nobody will ask you to memorize these equations, but we need to know how to use them. What are the units and what are the limitations? Because there are some equations are, for example, we're going to see Q is equal CIA. This is the rational formula to calculate the runoff for any given watershed. So you will find this equation, either uppercase or lowercase for I. You will find that we do have some limitations. So units, I will say units number 1. This is something I need you to pay close attention to that. Units and limitations or restrictions as far as using these equations. And units converting from one system to another or from certain given information to another is very, very important. For example, if you get a chance to print mini exam number 4, for those of you who get a chance, let me just go over some problems. I include the solutions, some of them I don't. I need you to work it out. This is why I need to challenge yourself. And as I said, that the more that we challenge ourselves, the better the chance that for passing this exam, because we need to do mistakes here. We need to do as many mistakes as we can do here. Okay, if we have 0 mistakes, that's good. But if we did a mistake here, we can correct it. But if we did a mistake on the actual exam, obviously, is not going to be good news. So here, for example, I'm reading this just in case. A pumping scheme requires the water to be transported from a river at an elevation Z1 is given, to a reservoir at elevation Z2 is given, the Q is given, and the Q is given gallon per minute, GPM, either uppercase or lowercase, GPM, gallon per minute. The pipe has a length of 1500 feet. The diameter is given. The pipe is made of concrete and contains gate valve, half open, 2 standard elbows, and a pipe exit loss. Okay, and he said using Hazen-Williams formula to estimate the pipe friction loss. So a lot of information, and during the exam we need to understand what are the given information and the units for each parameter of and the units for each parameter. If you are able to draw a picture or a sketch, I call it translate into English. When we translate into English means that you are converting, translate into English is to get this wording into a free body diagram. If there's a free body diagram can be drawn, free body diagram, into cash flow diagram if it's engineering economics problem or a benefit cost ratio, or it could be a sketch, or if you like to call it illustration, or just a diagram, whatever the appropriate name you would like to use. This will be a good idea during your studying, okay, or your preparation, because the more you prepare or you convert the text into illustrations or sketches or diagrams or cash flow diagrams and so on, the better the chance for understanding or fully understanding the problem. So he said that there is a river here. Okay, let me get my camera down a little bit. Okay, and there is a pump here. And this pump is taking this water from here, and it's pushing this into a pipe that it is 1500 feet, but the pipe has some kind of a valve somewhere, gate valve, and the gate valve is half open. And he said that it has 2 standard elbows. For some reason, we have an elbow and another elbow. Okay. Try to draw as much as I can here. And it does take the water, okay, to some kind of a reservoir. And this is a pump. Did I miss anything? 2 standard elbow pump exit. Okay, the exit is here. This is the exit. And he's asking the first portion of that, or the first part of this problem, or the problem number 1, because I repeated more than once to get more additional problems to be added. Here is asking for the friction heat loss. As you know, the losses are classified to be major losses and minor losses. Major losses, this is due to friction. There is a friction between the liquid and the carrying pipe or the carrying system in general. So there is some kind of friction between the liquid and the surface of the pipe, and the amount of the losses will depend on the type of the liquid, the temperature of the liquid, the nature of the surface, the type of the surface, and so on. Many factors will affect the amount of the major losses. The minor losses, it is a function of V squared over 2G. So it is a function of V squared over 2G. By the way, this is called the velocity head. As you know, there are two let me start with this first, and after that I will jump on what I'm trying to say. So minor loss is a function, and we write it as a K V squared over 2G. Some book they're using letter C, V squared over 2G. Certain constant, a constant, okay, that is a function of the velocity head. This is called velocity head. And these constants, the K or C, they have some tables available in almost every geotechnical, any hydrology textbook. And they giving us if this is half open or full open, entrance, exit, elbow, name it. Okay, so this is for the minor. But for the major losses, sometimes in the problem statement, they can mention the method that should be used for computing the friction losses. For example, here, he's asking you to use Hazen-Williams formula. And this is the equation that's available in textbooks, including my book. And it's just a matter of to substitute for the parameters of this equation. You will get what will be the amount of the friction losses. Came to be 118.119. The answer here, by the way, I changed it this morning. So the answer is A, because 119 is the closest one. So I changed the answers more than once this morning. So, and I will correct that as we proceed, if there is anything that need to be corrected. So sometimes they mention that, and sometimes they did not mention at all. But the problem itself, it can tell us what he is asking us or what equation should be used. Okay. And we are going to see some of them during today's discussion. So this is the equation. The H sub L, the system head loss, using this equation, Hazen-Williams. He mentioned the type of the pipe. He said that the pipe, a certain material, the pipe is made concrete. And if you look to any table given, including this, you'll find that for Hazen-Williams coefficient, the C in this equation, is given to be 130. And I give you the reference from my book. Those who have my book, you will find this or any other book available in the market. You will be. This is I'm referring to my textbook since this is the one I'm using in my classes. So you will find that the EQ is given to be 1,030 gallon per minute, GPM. So the Q, so the equation, the H sub L, is equal to 4.72. L is the length in feet, and C is the Hazen-Williams coefficient of 1.85, and D is the diameter raised to 4.87. If you find a typo or a mistake in these equations I gave you, please let me know. It could be while I'm typing or whoever typed for me. So this is the equation. If you look to the units, as I mentioned that we have this here, it should be in feet. The diameter, it should be also in foot or feet. This is just a constant. And a Q is what? A Q is feet per second. So we need to pay attention to that because the end result here is going to be in feet. The head loss will be in feet. So a Q is given to be 1030 GPM, gallon per minute. I need to convert this to feet per second. So if you don't have handy book that it has the conversion factor directly, you can say that it is 130 gallon per minute. I will write it down like this. And I can convert this. I'm saying that how many cubic feet or how many gallons in 1 cubic foot. So I will say that 1 cubic foot, it does have 7.48 gallons. And this is minute. I need it to be second. So how many seconds per minute? I would say minute over 60 seconds. So if you look to this, minute will cancel with minute, gallon will cancel with gallon, and what is the end result is going to be cubic feet per second. So if you do this calculation, as I indicated, okay, you will find that this number here, if you multiply the gallon per minute times 0.002228, it will give you this number in feet per second, which is basically the 7.48 times 60. And let me double check very quick. Sometimes I do mistakes like anybody else. Okay. So in this case, it is 60 enter 7.48 times, and you get the inverse of that. This will give you this number, which is 0.002228. And this is a number that you will see it also in my solution. Here it is. Gallon per minute time. This will give you feet per second. But just in case, if you don't have this number handy, I don't like it to stack. Okay, I don't like to lose a problem because I don't have the conversion factor. It is better I put all of them. I believe I encourage all my participants in the class in the book number 3. I number my books because I have 3 books for the AM. So this is a civil ability practice exam and solution. It does have a summary at the beginning, and I said that please let us use the first page here. Or page number 3 to put some kind of I have units here, conversions for units, but if we can come up with a list, short list, that frequently used conversion factors, and here it is, one of them is number 4, for example, gallon per minute times GPM times this will give you this cubic feet per second. And we went up to number 11, and I typed here 10, and I said, okay, we can add more. 10, 11, if we can come up with a short list. There are some books available in the market, and I'm sure some of you are familiar with it, or maybe all of you are familiar with it, but there is no need to purchase a book, okay, just only for the units, because we are using a certain number of unit conversions, okay? So if we can summarize them in a short, in a short space, or a small space, or confined space, or somewhere, at least I can get access, or I can get access to it during the exam will be much better. And as all of you know that we have the 7.48, the one I mentioned, and we use this a lot in materials, especially for concrete. So we know that if you have 1 cubic foot of water, under the standard normal temperature, 1 cubic foot, 1 by 1 by 1. So 1 cubic foot of water. This was 62.4 pounds, which we call it gamma water. Gamma water is the standard we are using, or the default value we are using, 62.4. So if it's not given to you in the exam, we use this. Like other gammas, as we talked about, or we're going to talk about it in the future. So this cubic foot of water, it does have a certain, okay, certain temperature, let me put it that way for the time being. How many gallons bear 1 cubic foot of water? Okay. And this is what we're talking about. It is 7.48 gallons, or let me reverse it, or 1 over to make it. So, or 7.48 gallons bear 1 cubic foot of water. The same story, how many pounds bear a gallon of water? How many pounds? This also 8.33 or 8.34, whatever is convenient for you. So 1 over also, let me make it that way, or we can say that it is 8.34 pounds, okay, per gallon of water. And they are related to each other, as you can see from this, just that we have, if I have 62.4, and if we divide it by 7.48, this is supposed to give you this number here, which is 8. So this is supposed to give you the 8.34 or 8.33, whatever. 8.34 is the most common one, so 8.34 pounds per a gallon of water. And we need this later on, because when we calculate the water cement ratio, sometimes the water cement ratio can express as a fraction, or sometimes they expressed as how many sacks of cement per gallon of water. So we need to know that. So my point is, units are very important, and okay, and do the calculations, obviously the exponents here. So this is the CFS, cubic feet per second, we found, and the area, don't forget the area. The area is for any, okay, this pipe here, and don't hesitate to write it somewhere, even if I know you remember this by heart, but the cross-sectional area is equal by d square over 4, or it is by r square. R is the radius in this case. R is d over 2. I know we are using d a lot, and we are using r a lot. R, we use it in surveying or vertical curves as the, and R, we use it also for structures as the, so this R here is the radius. Okay, since I mentioned that, the other two R's, okay, R in geometrics, G2 minus G1 over L. Okay, this is for this general equation, y at any point is equal the y at the beginning of the vertical curve plus g1x plus rx squared divided by 2. This is vertical curve. This is the general equation, as you know. R is called the rate of a gradient change per station, G2 minus G1 over L, and the R, it could be a positive or negative, as you know, it depends if it's a crest or sag vertical curve. So this is another R. Another R, we use it also for the AM, which is a R, which we call it radius of gyration. Radius of gyration, which is given by this equation, square root of I over A. I over A, and I is a moment of inertia or the second moment of area, and the area is a cross-sectional area, and the R it must be in inches or millimeter because this to the fourth and this square take the square root. So this is here. This is a R, by the way, since I mentioned that this is a percentage per station, normally expressed as a rate of change, okay, or a rate of change of the grade per station, or a change, okay, in the grade per station, or the rate of gradient change per station, whatever name you would like to use. So D also, we use the D a lot in different locations, but D is in this case is the diameter. So the area, don't hesitate to write it down just in case sometimes, okay, so this is the area. And obviously this is a continuity equation. A Q is equal V times A. All of us, we know that. A Q is equal V times A. From here, we can say that if I know Q and I know A, in this case, I can get V. So in this case, I can get V and we can calculate V, okay, as indicated here because we need it for another application later on or another problem later on. So this is the problem that I needed to be aware of. If you flip the page, you will find the same problem, but I'm asking for what the total minor losses. Minor losses here we're talking about. There is a pump, okay. We have a gate valve, half open, and we have an elbow, and we do have an elbow, and we have an exit. And if you look to any hydraulics book, you will find many illustrations to explain or to illustrate the type of losses and differentiating from minor and major losses. For example, let me bring a picture. I have it in my book, and all of you familiar with this picture, and it is not an invention. It is just, sorry, I wrote a lot on my, this is one of the figures, okay, I have a tank. We have a tank here, okay, or some kind of reservoir. We have an entrance. We do have a pump on the way, that we have a valve, we have an elbow, and we have another, okay, and no, there's no another elbow, one elbow and valve, and we have an exit, takes the water, okay. And this diagram shows the two important lines, the HGL and the hydraulic grade line and the energy grade line. So there are two lines. I need you to remember them in hydraulics and the hydrology, especially in hydraulics. So the two lines they came up with is the HGL and the EGL. So the energy grade line, EGL, and the HGL. This is the energy grade line, and this is the hydraulic grade line. And the hydraulic grade line, basically, it is the surface of the water. This line is above the surface of the water. And the gap or the difference between these two, by the way, is a velocity head, which is a V square over 2G. V square over 2G. I need you to remember that. V square over 2G. And this is why I believe, for those who are taking the class with me, in the book number 2, I have some questions. I will be glad to go over some of them today. About 50 questions. Here it is. In fact, I'm lucky. Here it is. Question number 48. HGL is always above or below the center line of the pipe by a distance equal to, and velocity head, pressure head, velocity head, or so on, and give you something else. So again, simple questions like this, we need to be aware of the relationship between lines. For example, another question also in the same book, okay, the HGL. Okay, which of the following defines the hydraulic grade line? It is the HGL is equal velocity head minus the elevation of the pipe. The HGL is equal elevation of the pipe plus the flow rate. the HGL is equal EGL minus the pressure head, or HGL is equal to the, and so on. So we need to understand the relationship between these parameters, just in case if he asks you a conceptual question, or maybe a problem, okay, that it could be given to you. So the energy grid line and hydraulic grid line, and this is the velocity head. Okay, I will go back again to the problem. At least I will not lose the track of the. So problem number 1, we are done with it. Problem number 2 is asking you for the same problem, given information, asking what are the minor losses. Okay, and even I did not change the, because I copied this problem from, okay, so I will probably, when I send you the solution, because the minor losses, okay, it is only 17.9. This is a problem number 3, by the way. So I can say that here it is 16 feet, okay, or 16 only because the fit already, you can change that, 16, okay, and maybe 18, maybe 20, and maybe 22, just to give you. And in this case, the answer is 18. So I will change this answer to make it B. And in this case is 18 feet. So we said that the minor losses, okay, in feet, they are a function of V squared over 2G. Because I wake up this morning at 5 o'clock this morning, I thought that already I prepared this, and I said, oh my God, I did not let me prepare something very quick for you guys. So it is a K, constant K, or C, as I told you. This K or this C, it depends on the components in the system. For example, here, the table that, or in our problem here, we have one gate valve, half open, one elbow and the exit. So in this case, I will go to a table similar to this. Let me get the table that has the minor losses. And this is, as I told you, available. Here it is. Minor losses coefficients. And this is the equation that it is a C or K. And here are some values for C, minor losses coefficients. If it is globe valve, okay, fully open, half open, angle, all these things, you should have a table like this, and this table is available everywhere, okay? So if I'm able to get these coefficients from a table like this, I can add them up, and after that, and I know the Q, which already talked about before, so I'm repeating the same conversion from GPM to cubic feet per second. And this is area, and this is V right now. We need V right now. So if I added the 5.6 plus 2 times 0.9 plus 1. So this is the gate valve, half open, and these are the 2 elbows, and this is the exit loss. They came to be 8.4 total. So 8.4 times V squared over 2G, and we got this number here, and make sense? Now he is asking, you need to go and purchase this pump right now. Okay, this pump, okay, needs to push the water from here all the way up to here, from Z1 to Z2. Whatever the elevation, if this is the datum that in reference, so maybe the water, this is the Z1, takes all the way to Z2. So he's saying that what is the horsepower that you need to have in order to efficiently be able to pump the water all the way to the proper elevation. So this pump must be overcoming what? The elevation head, because there are three heads. We have elevation head, and we have a pressure head, and we have the velocity head. Those are the three parameters that we are using in Bernoulli's equation, as you know. And basically, Bernoulli's equation, the elevation head, which is Z, a pressure head, which is the B over gamma, and the velocity head, which is V squared over 2G. And this is why you will find that the equation, the Z or Z1, if we are comparing, or Z in general, Z plus B over gamma plus V squared over 2G, those are the three parameters that we applied or we include them at any given point along the system. And this is why you will find there is a general equation. And again, this is also in most of the books or all the books. This is a general equation, for example, that the Bernoulli's equation, which is also known as a conservation of energy equation. So this is Bernoulli's equation, which is the elevation head plus the pressure head plus the velocity head. But if we'd like to have all the parameters, including the possibility of having a pump or a turbine, plus the losses. So in this case, we are talking about deflection loss. If there is a turbine, if there is a pump, and if we have all the minor losses in terms of V squared over 2G, so we can write this equation here. So those are the three parameters that we need to pay attention to, plus any possibility of pumps or turbine, and also the losses that we are talking about. So the going back to the problem number 3 of this is asking what is the pump head. Okay, so basically we need this pump to overcome all these. Okay, the elevation head and the pressure head and the velocity head, all these things. So the losses we already computed in problem number 1 and problem number 2. So I broke down the problem. So this, to make it 6-minute problem. Okay, so the 118.87, this is the friction losses, friction loss. And the 17.9, we just calculated 17.9, this is the minor losses using this equation V squared over 2G times the coefficients C we got. So basically, if we apply the equation at both ends, if you like to call this is number 1 and this is number 2, location 1 and location 2. I can apply the equation here and the equation there. So here are the parameters. The energy equation or Bernoulli's equation. Okay. I probably the order Z1 is supposed to be first, but that's fine. B over G V square plus horsepower is equal this. Turbine or H sub L. So I have Z1 and Z2. Okay. And he mentioned here something that the pressure term and the velocity term, okay, are zero, because we are assuming that the water here velocity, this is atmospheric pressure, so the pressure is zero, and again the velocity is also zero because the surface of the water, we assume that it is. So in this case you will find that the difference between the elevations plus the total 136 feet, which is the total head loss. This is the amount of head that the pipe should overcome this. So if we have the efficiency of the pump 70%, 80%, we can determine how many horsepower, because our ultimate goal is to get the horsepower that would be required in order to deliver this or do this for me or for whatever the project is. And this is how they determine the horsepower required, okay, for any given pump. So this is some kind of problems related to the Bernoulli's equation and minor losses, major losses, and so on. So I hope these are reminding you with the and it seems to me there is a question from one of you. You are very welcome. Normally, when I see something from you here, I hold it until the end. Okay. The total loss, it is a 118. Yes. Did I do this wrong? Okay. Our friend is saying me. No, my intention was okay. It is sorry. The total minor losses. Yeah. Still okay. Mohammed. Okay. The total minor losses is not the total losses. The total losses is the sum of the two. You are completely right, but it's wording correctly. The only thing that I did, okay, that I didn't change the answer, because these answers was originally related to this problem here, but the total minor losses, so it's still correct. No, the wording is still correct after we change this number here. So, okay, so I needed to be aware of that, because these things, it could be a target for a question on the exam or something like that, okay? Let me jump all the way to the end, to problem number 24, okay? Number 24, okay? Let me give you 1 minute only to do it for me. Problem number 24, if you don't have the problem with you, here it is. Okay. The runoff from a new highway facility is collected in a storage basin and is released slowly through a circular corrugated metal pipe. The Q is given, the estimated flow is given to be, or the Q is given to be 43 CFS. The slope of the pipe is given and the N is given. The moment that I see N, that means that he is asking me to use the famous Manning formula. So a Q, as you know, is equal V times A, the continuity equation. And V, as determined by Professor Manning, is 1.486 divided by N, RH 2/3 the square root of S, and I will multiply for the area here. This is a circular pipe, so they are expecting that this is a diameter we're looking for, and here is a Q, is 43 CFS, and the slope is given S is equal 0.001 foot per foot. Sometimes they give you the slope as a percentage, by the way. Okay. So it's asking if I know the Q and I know the slope and I know the N. If it's not given, there are some tables available and depends on the type of the pipe, the coefficient or Manning's coefficient should be available for you. So here I have almost everything except the diameter of the pipe. If I get the cross-sectional area, it will be piece of cake. The RH, as all of you know, the RH is the hydraulic radius. Hydraulic radius. And by definition, the hydraulic radius is given as the area of the flow, or the flow area of flow divided by the weighted parameter. Weighted parameter. And sometimes they can use this definition to ask another question. I will address it after this problem, but let me finish it first, and after that we will see. And you are very welcome to email me if you feel there is any topic or subtopic that is not covered to the depth of your satisfaction, or you have something unclear. Please email me and I'll be glad to address it. So the hydraulic radius, the RH, hydraulic radius, the area of the flow divided by the weighted parameter. And we have a lot of tables and charts and figures, and they did a lot of work for us, the scientists and the professors. So for a circular pipe, as all of you know, if the diameter is D, so the RH is equal the area of the flow, which is pi D square over 4, divided by the weighted parameter. In this case, the circumference of this pipe is in fact the weighted parameter. So the pipe, the flowing full, so this surface here is the weighted parameter, which is, in this case, it is pi D. This is a parameter. So in this case, pi D will cancel, so this will give you D over 4. So when the pipe is flowing full, all of you know that the hydraulic radius for such pipe is D over 4. Also, if the pipe is flowing half full, by the way. So such that this here, normally we use this as a lowercase d, which is D over 2. Okay, so in this case, the weighted parameter will be only half of the circumference. But since it is half of the circumference and half of the flow, so it is pi d square over 4 if this is full, but I will take half. And pi d is a circumference, but it is half. Half will cancel with half, and you ended also with d over 4. Okay, so if this pipe is flowing, okay, half full, so in this case, and the 3/4 and so on, I will show you a couple tables. They are available in most of the hydraulics textbooks. I rely on this book. Probably I showed you if I have it here. I don't know where is the book. No, I don't have it. No, here it is. One of my favorite books, really. And there are many good books. Don't take it personal, but I remember this book very well because this is the first semester for me when I came from Egypt to the United States. So fluid mechanics with engineering application by very nice two professors, one at Stanford and one professor at California Institute of Technology. Two of the finest school in California. And I still like them. I still like this book very well, and one of the finest book available in the market at that time. I don't know. Right now we have tons of books, and I'm not saying that, but I am so influenced by this book too much. Okay, so in this case, it is d over 4. So if going back to the problem, and probably some of you already maybe give me the answer. Thank you very much. Unless you have a question for me. So if you look to this problem, you will find that we do have some kind of Ray got something, good news. Okay. So, and Max also got some numbers, good news. Both of you are correct. Thank you very much. So in this case, it's just a matter of plugging the number into the equation. The only thing that I needed to be aware of, the exponents and log and the anti-log and all these things. And please use whatever calculator you are going to use. Personally, I use the HB, but there is some other calculators available in the market, and Casio and TI and name it. All these calculators are very good. I'm not against any calculator, either this one or Casio. They came up with the new one. TI is also. It depends on whatever your preference, but. I purchased, even some of you emailed me. I did not, some of you, because I purchased a bunch of them for those who are taking the class, because especially when we're talking about geometrics, degrees, minutes, seconds, and all these things, solving quadratic formula, all these things are so easy, and I can give you some kind of a short training about that. I know there are full trainings, okay, for the EIT or the FE, but I purchased a bunch of them, and some of you already told me that, can you send it to me? And I did not send it until now. Forgive me for that. I will be glad to send one to you. Okay, I have no problem with that. Okay. So I have a box here next to me full, and forgive me for that I did not. So if you look to this problem here, very quick, problem number 24. In this case, you can say that if I know the equation, here it is. The equation is just a matter of, if this is 43, which is Q, is equal 1.486 over N. N is given to be 0.025. And the RH, which is hydraulic radius, which is D over 4, and this is 2/3, and a square root of S, which is given to be 0.001. And the area is equal by D square over 4. So the only unknown here, I know this, and I know all the parameters. So in this case, solve for D. It's just a matter of exponents and all these things. 5 foot is a good answer, and you will find that the answer is B in this case. So 4.99 or 5, it depends how many decimal places do you carry. But we need to be aware of that. Another type of problems that related to the hydraulic radius which is the most efficient cross section. Okay, thank you very much. Okay, the most efficient cross section. As you know, open channel flows. Okay, all these are open channel. Okay, they have different shapes and different configurations, and the question is, so if this is page number 4, the most efficient section or cross section for an open channel. For example, I believe after I finished this morning the mini exam, the one I sent it to you, I opened another binder and I found a lot of problems, and I will be glad to include it later on in another mini exam or so. So the most efficient section is the section that will maximize the flow. So the most efficient cross section, by definition, because a pipe, it could be, or sorry, an open channel, sorry, it could be a rectangular pipe, again, rectangular open channel, rectangular section, could be like that, rectangular or square they are, and the flow is, it could be a semicircle like that, or it could be a trapezoidal channel, and so on. This is the depth of the flow. So if you look to the equation, because most efficient, efficiency means the maximum Q. Maximum Q. If we can maximize the flow, so in this case, so you'll find that the equation in general Q, which is V times A, which is the one we just used, 1 over N, RH 2/3, the square root of S, and multiplied by the area. So in order to maximize Q, N is a certain constant. We have no control over it. Materials, yes. Materials, whatever material we are using, we have tables for either concrete or asphalt or whatever the material is. So the material, it does have a function. The smaller the N, okay, the larger the Q. But if you look to the RH, you will find that the RH is the definition we just mentioned. The cross-sectional area of the flow, not of the pipe, or the flow cross-sectional area, divided by, sorry, I wrote it that way, divided by the weighted parameter. So in this case, if you look to the RH, and let me write it here again, the RH is flow area over the weighted parameter. So in order to maximize Q, I need to maximize this. Yes, the slope, the steeper the slope, the better. The cross-sectional area, the bigger the area, the better the Q. But the area and the RH are related to each other. So they look to this, the RH. RH will be larger if the weighted parameter is getting smaller. So the smaller the weighted parameter, the larger the RH, the larger the Q. Are you with me? This is the concept of developing what are the most efficient cross sections. And there are some tables. I'll be glad to provide some of them to you. And we can derive the equation. But I do have a problem. I found a problem this morning, and I can write the problem right now, and we can talk about it after the break. Okay. An open channel, okay, is to be designed to carry 1 cubic meter per second at a slope S of 0.0065. The N is given to be 0.011. So this is what is given. And to find the most efficient width, for a rectangular channel a rectangular section is most nearly the most efficient width for a rectangular channel is most nearly, and he gave you 4 answers, A, B, C, and D. One of them is 400 millimeter, mm, and 668 millimeter. And I know you probably hate the SI units, but we have to be ready for both because the exam. And finally, 868 mm. Okay, and let me show you the problem and with the 4 possible answers. And 1 meter, by the way, 1 meter is equal 1000 millimeter, or 1 meter is equal 100 centimeters. Okay, so those are the SI units that I know. I remember when I came here to the state in 1982, and back home in Egypt, we follow the system, the SI system meters, and so on. So when they say that there is a bridge 500 feet, So I don't know if this bridge is really long or short. I don't get a feeling of a 500-foot bridge or 500-foot bridge. So I have to convert the foot into meters to see the length of the bridge in meters. At least I can, oh yeah, this bridge is too long. No, this bridge is too. So I know it is SI units is not really okay. So let us take a few minutes break, try to get some fresh air. As I always joke with you guys, I don't mean anything other than just reminding you and reminding myself that we need to stay healthy. Just get fresh air without any coronavirus, please. Just fresh air, pure fresh air. Okay, no air with any viruses, please. Okay, so 10 minutes from now, we are going to meet again to continue our discussion. If you like to grab a cup of coffee and come back to work this problem, you are very welcome to do so. So, so right now is about 10:15, so 10:25 we are going to meet again. Thank you very much. Enjoy your break. Thank you. Okay, welcome back everybody after this short break, and I hope that you enjoyed the break. And so the most efficient section, the one we're talking about before the break, is the one that it has the least weighted parameter, because in relation to the cross-sectional of the flow based on this relationship. So if you look to the weighted parameter for these shapes, and we can go over the equation and derive the equations. But as I said, that there are some tables available for most efficient sections. I'll be glad to send you this table. The idea, if you look to the circular section, or half a circle, sorry, the semicircular cross section for a pipe or for an open channel, and assume that the flow is all the way up to here, and this is, I will call this is d/2, which is the depth of the flow. Okay, half a circle or semicircle, that means that this here is d, the diameter. And if you look to the depth here, and the diameter, you will find that the RH is exactly as we did before, which is by d square over 4, but this is half a circle, over the weighted parameter, which is by, let us use the lowercase d, by d, and it is 1/2. So this is the d/4, the one we talked about. If you look to a rectangular section, and assume that the depth of the flow is also d/2, and assume that this is also d. So the RH is equal to the area, which is basically, it is d/2 times d, the area, the cross-sectional area of the flow, assuming that the flow is also at a depth of d/2, divided by the parameter. I will go down d/2, plus here is d, plus d/2. So this is d square over 2, and this is d/2 and d/2. And this is, so it is 2d. So d will cancel with d, and you will find this is d/4. Is this correct? So it is d times d/2 divided by the weighted parameter d/2 plus d. So far so good. So the hydraulic radius at the end, we ended with the same. But if you look to the weighted parameter, the weighted parameter here is d over 2 plus d over 2 will give you 2d. But if you look to the weighted parameter here is by d over 2. Okay. So if we look to this, half of by d, which is the 3.14.5 times, is about 1.57 d versus 2d as far as the weighted parameter. As far as the weighted parameter. So this is a weighted parameter for both. And as I said that this is d over 4 and this is d over 4. So imagine that we came here and we draw a half a circle here. I'm telling you this, at least you can understand the concept, how they come up with the concept of that. So in this case, the weighted parameter, if we draw a half a circle into this rectangular section, so you will find that the weighted parameter here in this case for this is like this, which is the one I was talking about here. So the weighted parameter for the half a circle, semicircle, it is 1.57d versus, okay, the 2d, which is for a rectangular section. But as you can see, this half a circle, it fits here. And this is the best we can get. First of all, this is the best on the most efficient section as far as the relationship between the Q and the weighted parameter. But in order to build this, is not just the most efficient section as far as the Q, but we look to the other parameters, which is the construction cost, and the time that we are going to spend to do that. Which one is much easier to build? This or this, the rectangular section? Obviously, the rectangular section is much easier to put the forms and is easy to build, and we ended with the hydraulic radius of the same. Okay, so and this is a concept for the most efficient section. In fact, if you look to the rectangular, the trapezoidal section, which we can derive it also the same concept, the trapezoidal shapes, you will find that this section as far as the weighted parameter also, it came from a complete hexagon or hexagon. Okay, and we took half of it and we built most of the channels like this, by the way, because of the efficiency of the section. So for going back to the problem, the one I put on the screen here before we go to the break. And I don't know how many answers you got, how many of you got the answer, but I believe after this explanation here right now, when I compare the most efficient section with a rectangular section, right now he is telling you He is talking about the most efficient rectangular section. So the most efficient for a rectangular section is going to be when the depth is half of the width. I need you to know that. So if this is, after that became piece of cake, okay? This is the depth, D, and this is 2D. Exactly as the analogy I made it here, okay? So I used D over 2 and D, which is when the width for a rectangular section, when the width equals 2 or twice the depth, I needed to remember this is the most efficient section based on the discussion that we had. Knowing that became piece of cake. So let me give you another 2 minutes to see what answer you are going to get based on this relationship between the width and the depth to get the most efficient section for a rectangular open channel. And I'm waiting for an answer. Slope is given 0.00. Make sure that I copy this correctly. And the N is 0.011. And the Q is given to 1.0. Yeah, 1.0 cubic meter per second. Okay. I know it is a 6-minute question, but you are under relaxed environment, and the relaxed environment normally okay. Any answers? Okay, to proceed, let me do it very quick with you. So in this case, we do have the Q is given to be 1 cubic meter per second. So the equation, Manning's formula for the SI, okay, it seems to me I got an answer. Let me just grab it very quick and see if you are agree with me. Okay, let us see. Probably I did a mistake if the answers I provided are not. I said that the closest one. So a Q is equal V times A is equal 1 over N of the RH 2/3 square root of S times the area So if we are going to take the concept I just talked about, or the conclusion after I explained the concept, that the most efficient rectangular section will be when the depth is half of the width, okay? So in this case, a Q is given to be 1 cubic meter per second equals to 1 over 0.011. This is N. And the RH right now, what is the RH? We said that the RH is equal to the area, which is 2D times D divided by 2D plus D plus D. So it is equal to D square over 4D. Okay. Make sure that 2Ds, okay, 4Ds. So this and this, so it is equal to D over 2. Using these notations, D over 2 or D, just whatever you would like to, I use D for the depth. So in this case, the hydraulic radius is D over 2, okay, 2/3. The slope is given to be 0.0065. Is this correct? Did I give you the right slope? Yeah, 0.0065. And the area is 2D times D, which is 2D square. So this is the equation that we are going to solve for D. Okay, unless somebody found this is the RH, make sure that. So if you get a D around 870 or 868 millimeter mm, because this is in meter, by the way, don't forget to convert after you get the D multiplied by 1,000. So, or if you get it out around 868, which is answer D, this is, unless I did a mistake, you can find out if, solve it and let me know if this is what you are getting. He got an answer A, some of you get an answer A. No, look at it again one more time. Okay, my answer is not the answer. Okay, I used King's method, okay, table so and so. And unless I because I change the numbers sometimes. Let me look at again. I don't like to spend the time here to figure this out. Unless I change something here. Let me see. Since you mentioned King's method, I would like to talk about it very quick. So, I don't like to spend the time to. It will take a minute, but try to find out, and we'll see if you are getting the same answer or not. I'll put a question mark next to it. But this is a concept, okay, for the most efficient section, and the most efficient section must be the section that it has the minimum weighted parameter, as we explained for rectangular sections. This is the our friend mentioned about the King's method. Yes, King's method. Professor King, and during the break I will work it to see if this number is, and if it's not correct, if the answer is A as our friend suggested, I will be glad to correct myself here. King's method, Professor King came up with two K's, K and K prime. He called them the conveyance factor. And again, most of the hydraulics book, if not all, they have this. And let me show you the summary I provided, and it does have the King's method as I explained in the class. I'm sorry that my book is a little bit. So King's method is using a K, and this K is different from other Ks, by the way. He called them conveyance factors. And he gave us the tabulated values listed, and I will show it to you, and if you don't have it, I'll be glad to scan it and send it with my. So the depth of the flow, we'll call it D, and the bottom width here is B as in boy, and the slope could be given in terms of theta or in terms of horizontal and vertical, 1h. So the equation given as Q is equal K times 1 over N times D 8 over 3 times square root of S. This is the equation that Professor King used it for the K. And we use it here for a rectangular or trapezoidal and V, by the way. This could be used for a rectangular, and I'll show you the table. When the angle theta is equal 90, this is 90 degrees, right angle. Or we use it for a V. Expect a V also maybe on the exam. In fact, when I was looking again this morning, I found that I do have a problem. I have one of the exam problems I gave before. Let me see. I think I saw it this morning. Here it is. Yeah, here it is. Yeah, one of the problems, it is a V, okay? Water flow and triangular steel channel, okay? And the velocity is given, and we need to get. So it's a very interesting problem also, the triangular channels, okay, or the V channels, if you like to call it. So the V or the V and the rectangular. V, okay. It could be a target for a question, and I'll be glad to include this problem, okay. So Professor King said that if I have the ratio, call it X, okay, which is D over B, the depth over the width, and the angle or the slope, the horizontal to vertical, I can get some kind of a constant or a factor, he call it conveyance factor. For rectangular channels, we use it when the theta is equal 90. So we have only one column for a rectangular channels. Okay, when the angle is 90. Okay, so, and this is the value of the K. And the equation is going to be, as far as the V channel, because this is the width B, and this is the depth of the flow D. Obviously, we do have for this here is 0 here. The width here is equal 0. Okay, this here, the width is equal 0 in this case. Okay, so he is saying that, or the table has one specific number, which is infinity at the bottom here. Okay, the V, okay, this ratio D over B, which is D over B, he call it X. X is equal D over B, okay, which is the depth over the width. But since B here is equal 0, this is the depth of the flow. This is D, and B here is 0. So when you take this X, D over B, D over 0, we call it infinity. And this is why we are going to use the last row in this, which is infinity. As you can see here, probably, sorry, the picture is not very clear, but let me just get closer. And here it is, infinity. So we are using the last row for the infinity. Okay. So the footnotes at the bottom of this table are very important. When I send you, probably I will also include it just in case. And obviously it will not be really having all this. That for rectangular channels, use the 0. For V notch triangular channels, use the row of infinity. And the Q must be, all these are the US customary units. And for SI units, a Q in cubic meter per second, D and B are in meters. Divide each table value by 1.486. And this is why I will ask the engineer, one of you, he said that he used the King's method. Did you convert this? Did you use this conversion here? So probably if you take the 400 millimeter you are talking about, okay, maybe I don't know. I will solve it during the break, as I told you. 1.486. So maybe if this will be the source for maybe this. So we need to pay attention to that. This could be a source for an error, unless you already did. And as I said, that I will solve it and I will see if the answer is 400 or the 868 as I suggested, and we'll come back to this. Okay. So this is something that I need you to be aware of that. So the other table, by the way, okay, that's fine, Max. I will look at it since you already considered the. Okay, I will look at it. Probably my answer is the one. My suggested answer. Let me put it that way. The other table, by the way, is the K prime, and also the K prime in the other equation that Professor King. So there is K and K prime. And the K prime is given in this equation here. A Q is equal K prime 1 over N times B as in boy 8 over 3 square root of S. Those are the two equations that we use it for King's method, equation number 1, if you like to call it, equation number 2. So when you receive my notes, you will look at it. And this here, we use it, by the way, for determining Q or D. This is to calculate to get Q or D given B as in boy. This one here, which is a K, this is we use it when the to calculate Q or B, Okay, this to get or to calculate to get Q or B as in boy, okay, when D is known, when D, okay, is given. So I need you to be aware of that, what is given and what we are looking for, so we can use these in order to do this, okay? So King's method, sometimes we use it. It could be very helpful for certain application or certain problems, but not necessarily that you have to use it. It's your choice. If you okay, that's fine. I will look at it, my friend. That's fine. So this is what I needed to be aware of. Another thing that also included in the mini exam, a problem related to problem number 7. Problem number 7. Problem number 7. Water flows through a circular conduit of 42-inch diameter. Okay, and this is always the inside diameter, by the way. So it is 42-inch. The maximum flow, the maximum flow will occur at a certain depth. So they are saying what will be the depth? What is the depth in order to maximize the flow? They came up with tables and the charts. So for this type of problems, if you are giving a scenario like this, so you can look to the either tables or a charts. One of a chart that is very, very famous, which is published by the ASCE, because when I flip the page, this is a very famous chart that we discussed it in the class for circular channel ratios. And this is published, as I told you, the ASCE way back. Somebody published this in the ASCE of the American Society of Civil Engineers, 1969. And this a chart or this figure, it shows the relationship between the parameters that we use it for circular channels, and also the parameters are given here. The depth, the diameter, the inside diameter is D, the depth of the flow is D, and the angle theta, and all these things are given here in the hydraulic radius. The only thing that probably they are not using the R, they use the R without RH. So I added the RH here, H to the R, to make sure that this is not the radius. So this is the hydraulic radius. So I prefer to use RH as most of the textbook they are using RH for the hydraulic radius. So we could use this, okay, in order to get what is the maximum flow. And we look to the graph, for example, this is a charge Q, this color here, and we took where is the maximum will occur. The maximum will occur at this peak here, and after that the flow start to decrease. So, and we draw a horizontal line, and we got the D over D. This y-axis here is the depth of the flow in relation to the diameter of the pipe, and we ended with a number about 0.94 or so for the problem. So if this is the case here for problem number 7, I'll say that the maximum flow is at D over D ratio. Let me use the same D over D of about 0.9. We can say 0.94 or something like that. 0.94. So from here we can get the depth of the flow to be about 94.94 times 42 inches. And if you do this calculation, you are going to get something 0.94 times 42 will give you about 39.48 inches. So probably I will pick the answer, I will pick the answer C in this case, which is the best answer I can get. In addition to the chart I am showing you, this chart here, and the title of the chart is Circular Channel Ratios. You will find that the same could be obtained by series of tables they provided to us. And there are two famous tables also, they are available. This is one table, for example, in my book on page 149, and I'm referring to book number 3 always, which is one has the most comprehensive and updated or recent or the most comprehensive summary. So you will find that the area, weighted parameter, and the hydraulic radius of partially filled circular pipes. So if you open in a hydraulics book, you will find that. And again, they are showing the D and D, the depth of the flow and the inside diameter, and the D over D ratio. And there are some parameters here like area over D square, weighted parameter over D. This is one chart. If you flip the page, you will find that there is another chart also, okay, the flow ratios and velocity for a circular open channel, D over D, and all these things. And we can use this in order to get the Q over a Q full. Here it is. The last column here, they have a Q over a Q full, okay? So a Q over a Q full, you'll find that will be maximum. Okay, this number is increasing until we hit 1.0756, and after that it starts to decrease. So we pick the maximum. This is a maximum, a Q over a Q maximum, and I moved horizontally to get the ratio between D over D, and we ended with almost the same number, which is 0.94. So in this case, we can use this chart in order to get what is the depth of the flow when the pipe, okay, is flowing full, or to maximize the value of the Q. So this is another type of problems that I needed to be familiar with. So I will include all these charts with my notes when I send it to you, or scan it and send it to you. Okay, so this is something that I need you to be aware of. The other, let me just make sure here I am. This is page 6 here. The other problem given in the mini exam, number 4, the one we are talking about today. Let me get it here because I have a lot of paper around me. It is on the same page, by the way, the one when we solved the last problem, I believe. It does have something, one of you asked me to talk about it. Maybe in the future I can talk more, but just to give you the two definitions that sometimes a little bit can cause a little bit of, so the last problem, the 24, let me grab a question, or somebody maybe have a question for me, or an answer or a correction. Okay, thank you very much. Yes. Okay. Something related to, and I left the solution, problem number 23 of the same mini exam number 4. It is a foundation problem, but since some of you already emailed me talking about that topic, a continuous footing, it is 2 feet wide, and it is 3 feet below OG. We have a continuous footing. And the depth here is, which normally call it D sub F, by the way. Let's use uppercase, since uppercase is the one I use here. The depth D sub F, and this is given to be 3 feet. And the width here is B as in boy, 2 feet. And he gave you the gamma unit weight and the cohesion C. The angle phi is given. And he gave you the parameters, the N sub C and NQ and N gamma. N sub C, NQ and N gamma, which is the bearing capacity factors for the angle phi, whatever the angle phi, the angle of the internal friction. So if you look to the problem, he's asking what is the net. The word net, it does have a meaning, and this is why I made it a boldface. And the allowable, also I underline it. So the thing that I needed to pay attention to, the terminology, and looked for the keywords in any given problem. Keywords. Here he used the word net. He used the word allowable. Okay. Because we know the bearing capacity we have what is known as the ultimate bearing capacity. We have allowable bearing capacity. And now we are going to add another one, which is the net. And the net could be net ultimate or net allowable. And we need to know the difference between all these terminologies, because as I told you that on the exam, one word make a difference. One word make a huge difference as far as So when Professor Terzaghi and Mirhoff, by the way, Professor Terzaghi, he is the father of soil mechanics, and Professor Mirhoff, they work together to come up with equations. Professor Terzaghi, GHI, I believe, GHI, if I'm not mistaken. Terzaghi, Mirhoff, or Mirhoff Terzaghi equation, but Terzaghi is more familiar, okay, or more famous as a father of soil mechanics and foundation, in fact. He did a lot of research. So they came up with equation to get the bearing capacity. What is the bearing capacity? Bearing capacity is the ability of the soil to resist the load, and we convert the load into stress. So if you do have any kind of footing, and this footing is carrying a load P, it could be dead load plus life load plus any other loads. This is a concentric load. Concentric means there is no bending moment. Concentric. So we are expecting this load, and let's assume that the depth of the footing measured to the base is d sub f. So because of this load over this area, whatever the area is, we have some kind of stress. Normal compressive stress, which is actual stress, which is B over A, because it's axial load. So actual axial stress. If you like to word the word axial here, I have no problem with that. So this is coming from the loads through the columns to the footing. But we do have a soil here. We have soil underneath this footing, and this is where the bearing capacity will come into the play. So we have some kind of a resistance. Going up. From the soil. Here we call this is a Q ultimate, which is the ultimate bearing capacity. Ultimate bearing capacity. This is the maximum stress that the soil can take. The word ultimate is a maximum. Ultimate, like if you remember in steel design, we have the epsilon versus sigma. We have this stress strain curve, go up to the yield, and go up the upper yield point, lower yield point, go the ultimate. This is F sub u, and this is F sub y. So this is the yield, and F sub u is the ultimate. Ultimate is the maximum, always. So the ultimate bearing capacity, as provided by Professor Terzaghi, Professor Mirhoff equations, this is based on the maximum. And one of the equations, for example, for this is a Q ultimate. Q ultimate, ultimate is equal to 0.5 gamma B and gamma, a plus C and C, a plus gamma DF NQ. This is the general equation for a strip footing, as you remember. And this is the basic equation for a strip footing. And the NQ, N sub C, and gamma, those are the bearing capacity factors. Normally, they give it to you in the problem statement because there are too many values available and there are many tables on the chart. So I think they will give it to you on the exam if they are going to give you a problem related to this. So so we know what ultimate is. What is allowable? If you remember in steel design also, since I have this, we have something here. We'll call it if allowable. Allowable. Okay? Or sometimes we call it sigma allowable, which is the allowable stress. What is the relationship between this and this, for example? This F allowable or sigma allowable is equal F sub y divided by the factor of safety. And if you remember my joke, the one I told you in the class, obviously this strain, by the way, this is inch per inch. And this is the engineering, by the way. Sigma is equal B over A, which is in PSI or KSI or Pascal or megapascal. And these are the engineering definitions. And I will explain this when we talk about materials. There is a difference between engineering definitions and the true definitions. These are the engineering stress, and strain. We're dealing with the engineering definitions, and I will tell you why we don't use the true definitions. Because we have a true stress and the engineering stress, a true strain and the engineering strain. So these are the engineering stress strain definitions. So the joke I was telling you that you build the bridge and the bridge log or the data on the bridge or the sign on the bridge, it said this bridge is also, is only designed for 10 tons. The maximum load or the capacity or the bridge log is showing 10 tons. And I told you that Mr. Mansour, he has truck, nice truck like this. And the truck and the cargo exactly 10 tons, but he got hungry and he stopped by McDonald's and he got 2 Big Mac. So right now he's carrying 10 tons plus 2 Big Mac. And he will drive over this bridge. Do you think the bridge will collapse? No. Not because of 2 Big Mac or because Mr. Mansour, he knows that the capacity is 10 tons, but he got extra pallet of oranges or extra pallet of N95 masks with him to deliver it to whatever the location is. They need more masks. So he exceeding the capacity of the bridge. The maximum capacity is 10 tons. But the bridge is designed here, not here. So if Mr. Mansour added another ton or half a ton, a little bit more, it was still within the acceptable range. And the bridge will not collapse. This is why you're using a factor of safety, which is a factor of safety must be greater than 1. Will never be 1. Because if the factor of safety is 1, I am here. And we call it failure is imminent. It could happen at any moment. So if Mr. Mansour decided to take extra half a ton and you design your bridge for F sub y, there is a possibility for failure. The same story they apply it for soil mechanics. They are saying that this is the ultimate. Can I get something less than the ultimate? Yes, here it is, which is a Q allowable. So the Q allowable is less than the Q ultimate. Here it is like this. Sigma allowable less than the ultimate, either this or this, for F sub y. And the Q allowable is equally Q ultimate divided by the factor of safety. I need you to remember all these things. Okay, while you're studying, I need you to understand the concept and the relationship between equations, such that if you pick a wrong equation, so right now we have the Q allowable is equally Q ultimate divided by the factor of safety, or the factor of ignorance, as some textbook they call it, factor of ignorance. It's only a couple books, I believe, or maybe one book. Instead of calling factor of safety, call it factor of ignorance, because we are ignorant. Because why we are using factor of safety? There are 4 or 5 reasons, as you remember from school, that we use factor of safety, because uncertainty of the load, or the variation of the load or loads, variation of the material properties, the approximation in the analysis, the mistakes or the imperfection during construction. They don't build the things exactly as you design it. So they introduce a factor of safety to account for all these things in order to be on the safe side. So this is what I needed to be aware of. So the word net right now, net. Here we are talking about the bearing capacity at this level here, at the bottom of the footing. The relationship between the net and the actual is gamma df, which is this number here. We subtract the weight of the soil. Okay, we need to get the net. Okay, we subtract the weight of the soil, gamma df, which is the soil pressure at the base of the footing. So the Q net is equal to Q ultimate divided, minus gamma df, which is basically, obviously this is concrete, but normally we use that gamma df, where gamma is the weight of the unit weight of the soil at that location, or at that level, or at that. Okay, and this is acceptable, which is the soil pressure at the base. So after getting this equation, you subtract gamma df, and this is why sometimes you will find it is written that way. And some of you ask me, what is this -1 here? -1 came from here, and after that a Q net, you get the Q net. But I need a Q allowable. So the net allowable is equal the Q net divided by the factor of safety. The factor of safety, he gave it to you. Is this correct? I hope so. Yeah, factor of safety is 2.5. Okay, and this is what I need you to remember. So maybe the terminology, and please pay attention to all these terms that I'm referring to in order to. Okay. Let me just bring more paper here, because it seems to me I used all the paper. And the okay, the equation I wrote this morning, the rational formula Q is equal to the CIA, which is known as a rational formula. This I is the rainfall intensity. And A, obviously, is the area of the watershed. And C is the runoff coefficient. Runoff coefficient. And all of you are familiar with this equation, and I'm sure that you use it many times. The most difficult part of this equation is how to estimate Q. How to get I. How to estimate the rainfall intensity I. There are more than one method, and I do have a handout. I don't know if I send it to you or not. I'll be glad to send it also. Hopefully, I will remember all these things. I have been promising you too many things, but I will do all my best to fulfill my promises. If I forgot one of my promises or I did not do it, please remind me, and don't hesitate to remind me once, twice, 3 times. You promise us this, you promise this, and I will be glad to. There are 3 methods in the handout that you receive from me, and the scientist, the hydrology scientist, they spend a lot of time to come up with modeling and methods and way to calculate that. One of them is what you see in this problem here. Problem number 10. Problem number 10. An urban watershed is shown, and the detail of the no, I'm sorry. This is not the right time. Okay, I will talk about the time of concentration after that. Problem number 12 first. Problem number 12. So the Q is equal CIA. We need to get what is the average precipitation for any given area or any given watershed. One of the methods is called Thyssen-Bologan. They divide the area. Okay, this is the watershed. That's considered in the study. We have A, B, C, D, E, F. A, B, C, D, E, and F, and G. So we do have some gauges at this location. Some of them, okay, at these locations. So one of the methods is to take this and divide by the number, and that's it. So if you measure the rainfall intensity at gauge A and gauge B and so on, the rain gauges located in and around a drainage area is shown. And instead of saying that, just I as an average is equal the sum of all these readings, the sum of the i's divided by n, which is get the average, which is mathematical average or the average or the mean. (2.1) plus 3.1 plus 5.2 plus 3.8 plus 5.4 plus 3.3 plus finally the 4.5 divided by the n, which is 1, 2, 3, 4, 5, 6, 7. So we have 7. You'll get a number. This method here, they said no. We're not going to, this is one of the methods, by the way. This is the average method, which is very simple. And we can calculate it and see how accurate or how close to the Thyssen-Bologan depends on or try to proportion the area or take into consideration the area of the so if we come and create another column here, the area is given. So if you sum the area, if you take all this sum here, somebody can do this for me very quick. I can do it. Unless somebody already did it, would be good. Here it is, my calculator. So it is, if we add all these areas, I believe 735 enter, 475 plus, 640 plus, 620 plus, 740 plus, 685 plus, and finally 1210 plus. I got 5,105, 5105, if my math is correct. If you multiply the rainfall intensity or the precipitation time the area, will create a column, which is, if this is column number 1 and this is column number 2, multiply 1 times 2. So they are saying that we are going to take the rainfall gauge value here time the area, the influence area at that location, the area of the Bologan. He create a Bologan, and I will explain it to you when you receive the handout. We divide, okay, connect all these points and take the difference and draw a perpendicular line, and when they intersect, I doubt that he will ask you about the concept, but the concept you will have it. But basically we multiply the precipitation time the area. So if you do that, you will get some values. Which is 2.1, for example, 2.1 enter 735 times, you will get 1543.5. And we can do this for the rest. I don't know if some of you already did this problem or not. It is 1472.5. And I believe I saw a table somewhere around me. I have these numbers to save time. Let me just, yeah, here it is. Okay. Okay, I found it somewhere. So this number here is 328.0, and correct me if I'm wrong, 2356. You are faster than me because you are younger than me, so the younger generation must be faster. 6 and 2260 and 5545. You add this column also. This column, the multiplication of column 1 and 2, will give you a number 20,401.5. This is the sum. Okay, using Thiessen-Bolligen, so the average the average fall intensity or the average precipitation is equal what? Is equal the sum of the I for A divided by the sum of the area. So you multiply the precipitation times the area and add them. So in this case, if you add all these numbers, and if they came up with this right number here, hopefully, or this number here, sorry, if it is right, that's good. Divide by the sum of the area, which is 5105. So this will give you the answer that they are looking for. If you know the concept and you get a problem like this on the exam, yes, but if you don't have the equation, even some problems are so simple, but we need to be aware of. So it is 20,401.5. You divide it by the total area. This will give you a number. Let me just get it very quick here. I got about 3.9964 inches, which is, I would say that it is 4 inches, which is the answer C in this case. Sorry, let me calculate C, not C and D. So this is C. If we just, for the comparison, let us look to the numbers, the 4.5 of it, 3.3 plus, 5.4 plus, 3.8 plus, 5.2 plus, 3.1 plus, 2.1 plus. And if you use just the arithmetic average, you ended with a number in 3.91 inches. Okay, so this versus this, you can see here the area or the influence area or the area of the Bolligen is part of the calculation, and this is why we got different. So if you compare this with this, you will find this is a purely arithmetic average, and this is just the application of, and this is the equation that, and this must be given to you because the area, obviously, normally we calculate the area, okay, and we connect all these, by the way, connect all these stations, we call them stations, okay, we connect all these stations, and after that, with any the line connecting two stations, we divide it into halves and draw a perpendicular line. And also here it is, we connect this to this and divide this into two and draw a perpendicular line. And these lines will intersect to create polygons. And these are the areas of these polygons, and we apply this. So this method takes into consideration the area that will be affected, or the area surrounding any measuring gauge A and B and C and all these things, or the ring gauges. So I needed to be aware of that, and when you receive the handout, you will be extremely happy with that. The stability issue are very important. Consolidation, by the way, consolidation also is very important. Problem number 19 and the problem number 20. And the problem number 20, because some of you indicated that also number 21. Those are, and also I have another problem, I believe, maybe at the beginning. Oh yeah, problem, here it is. A problem number 16, number 17. All these are consolidation problems. Okay, consolidation is very, very important concept, especially for those who are taking geotechnical in the afternoon. I included with the solutions, by the way. All these are problems. I left the solutions, okay, so at least to help you. So you have a bunch of problems, okay, they are related to oh yeah, problem number 10. Problem number 10. Okay, because I will solve this and I will give you a problem. I give you a quiz after I finish this problem. If we solve it right, we'll go to lunch. If you didn't solve it right, no lunch today. Okay, so let's solve this first. Okay, problem number 10. We have a term is called time of concentration. Which sometimes we use T sub C. Time of concentration. What is a time of concentration? We do have a proposed highway here to be built or to be constructed. And we are going to put a proposed bridge here or a culvert. A culvert means that a culvert could be a box culvert, it could be a corrugated. Something to let the water to go through this. It could be a bridge or it could be a culvert. It could be, even if it's a bridge, for whatever reason that we need to put a bridge. But a culvert is one I would like to talk about it. And we do have one complete book by the way talking about culvert design by the FHWA. So I need to get the Q here. So I can size this culvert. It is 24 inch or 36 inch or a box 4x2 or whatever box, okay, concrete box, precast normally, or it could be a corrugated pipe or concrete pipe. So I need to know the size. So this is where the I will show up. The Q is equal CIA. But the size of this pipe or this culvert will depend on the watershed, how much this area, and nowadays we have maps. So this is the watershed that will contribute to Q, to genetic Q. Based on the topography and the elevations, we know that the water will flow. All this area the water will come in any storm, the water will be coming. So the time of concentration is very important. Time of concentration. Which is the amount of the time that a drop of water will travel from the farthest point all the way up to here. How much time does it take? So the time of concentration, it is from the farthest point. And all books available in the market, they have some kind of definitions, and including mine. If you'll find that at the beginning of this book here, I put some kind of glossary and definitions, and normally encourage everybody to use only one concentration, like time of concentration. We need to concentrate our time during the exam to get one location for summary and definitions and equations. Try to, if you have a 3-inch ring binder and you would like to use it, that's fine, as long as you know exactly where your information. And this is the challenge during the exam. So I cannot claim that all these things are perfect, but if we go to the time of concentration to see if, I think I have a definition here, probably I mention it, unless I mark it, believe RST. I'm getting there. Here it is. Oh, I found it. I mark it. So what is the time of concentration? By definition, and I didn't invent this definition. I got it from the textbooks. I rely on the textbooks, school textbooks. Time of concentration, it is a time for water to flow from the farthest. Did I spell farthest correct? Yes, farthest point on the watershed to the gauging station. So the time that will take the water to travel from the farthest point must be the farthest point. And they developed many equations. Some of them are empirical formulas, and some of them are combination of mathematical plus. So we know the definition of the time of concentration, T sub C. And the problem here, problem number 10 of mini exam number 4, that an urban watershed is shown and a travel path for the most remote point in each sub-area. The details is given. So the length and the average velocity, and is asking what is the time of concentration. So we have area 1, area 2, area 3, area 4, and the water will flow as indicated here until we get out at G. G is the gauging station. This is the outlet. Or if we go to the definition of the time of concentration, to the gauging station. If you'd like to call it, this is the gauging station, I have no problem with that. Gauging station. So if we are able to calculate one of the empirical formula, by the way, which is very simple, which is that time is equal the length over the velocity. So we can calculate this point, from this point all the way up to here, and from here to here, and so on. So I give you the path and the length and the velocity. So if you can get the time t, which is equal the L over V for each. Let's see if I have numbers here or not. If not, it's very simple calculation. And I'm sure that you can do this in less than 6 minutes. No, I don't have the numbers with me here right now. For some reason, I can. Or it could be hidden somewhere under the bunch of, or the piles of. So, if you take the length, so it is 1600, enter, 3 divided, so it is, and the time, by the way, here, by the way, he needs it in minute. Be careful. This time here is in minute, okay? So these are seconds. So if you divide L over V, you will get, okay, so it is 1600, 3 divided, okay, and 60 divided, so it is 8 point, this is 8.89 minutes, and so on. And in this case, I will calculate the travel time from the farthest point, okay? So if you calculate the same story here, 1490, enter, 1.8 divided, and 60 divided, so it is 13.80, and the same story, probably some of you try to give me an answer. Thank you very much for your help, but I'm trying to do it with 7.36 and 1300, enter, 2.5 divided, 60 divided, 8.67. We're getting there. 1250, 2.9 divide, 60 divided, 7.18, and finally the 1510, enter, 2.5 divided is 10.07. Okay, so we calculated that. So if you look to AE and EF and FG, if we take this route, if this is the farthest point here, and see if this is the longest or not. So if you add these three, what you will get? So if you look to the route A, E, EF, and finally FG, so we are adding these numbers together and you get a number. Okay, so AE, which is 8.89, and EF is 8.67, and finally the FG is 10.07 plus. So this is about 27.63 minute. If you take the other route, obviously it will not control, but if you take this route here from here to here to here, or from here to here, or from here to here, you will find that one of them will control, and obviously the farthest point in this case. But you need to calculate that, because sometimes they can give you some numbers that it could be a little bit misleading. Could be, okay, and you may say, oh, this is okay. You have to calculate the time of travel for each path, and after that decide which one is going to be the controlling one, and in this case you will be able to get it. Okay, so as I told you that the correct answer is 27.7, by the way, which is this one here. So if you calculate all these paths here, you'll find that. So the answer 27.7 is the largest among all the paths. So the answer is D. Okay. So this is another type of problems that I need you to be aware of, which is a term of concentration. And the problem that probably in the future I will include it, maybe it's very similar, even much simpler than this. In the NCEES, I believe, if I'm not mistaken, somebody sent it to me, and I told them that I will discuss it during the class. And I will give you only 22 seconds to do it. Here it is. Okay, this is a problem in the water resources and the environmental BM practice exam book. And I believe I have something similar to this because okay, so what's the answer for this? As I said, that if we get it right, we'll go to lunch. If we didn't get it or we got it wrong, no lunch. What about that? Deal? Deal. Okay, so he gave you here a table, and he said that 3 contributing areas of a watershed has a time of concentration for runoff flow, okay, contributing, okay, to an outlet at point A. Okay, assume that the distance is given from A to B is given, and the velocity is given 3 feet per second. The time of concentration to be used for the design of the pipe BC right now. Okay, right now I am here at this point. So basically all the time are given here. So I have 30, 20, and 10. Since I know this length L as we did, and I know V, so 450 divided by 3 will give you 150 seconds. 150 seconds is 2.5 minutes. 60 and 6, yes, 2.5 minutes. So if you take the 2.5 minutes, the water will flow from here to here over this distance. 2.5 minutes, I will add it to this, to 32, which is the largest, 32.5, and this is answer C. Agree or disagree? Everybody got the same answer C? Okay, that's good. If this is the case, okay, I can include something similar to this. Okay, please work the rest of the problems and try to do your best. And I pray for all of you and pray for me also. And after 1 hour from now, I will go over the construction BM. So if you are construction BM, you are very welcome. If you'd like to come to 32.5, thank you very much. Yeah, okay, good. Thank you very much, Lydia, and all of you are doing great. And so the afternoon, as I said, that I will be I believe if I have many exams here, and this is construction, and here it is. This is what I will cover, or I will cover this afternoon. If you are like to come, construction depth. Sorry, as I said, I missed one lecture. So they have some problems. You already probably you saw them before, or you are very welcome to come and join me, and I will talk about a lot of things related to construction BM. Okay, some of them are related to the AM, which is the calculations for the quantities and the CPM and all these things. But you are very welcome, whatever is convenient for you. Do it. And if you join me already, I send you, by the way, I send to everybody, I send the mini exam. Tomorrow I will be here for transportation, and in the afternoon I will be teaching seismic, by the way, and I made the seismic also for free this time to help everybody. So do your best, and I will do my best. As I said, that as long as we are healthy, we are wealthy. As long as we are healthy, we are wealthy, and I hope that all of you, including myself, to stay healthy. And thank you very much for coming today. And after 1 hour, you are very welcome to join me again for the same. Yeah, okay. I'm sorry. Okay, I got a question. I'm not going to leave. How did we come up with 32.5 seconds? Let me just put it on the screen very quick. Here it is. Okay, so the calculations like this, let me draw it here, at least I can. Okay, so we do have the watershed. Let me include here, at least you can get it also. 1, 2, and 3. So the water flowing, and they said that we have a point A here. He gave us for this here, the time, for example, this is 10 minutes, and for number 2 is 20 minutes, and for number 3 is 30 minutes. This is the time of concentration calculated for each watershed, mean that the water that will travel from the farthest point of the watershed number 3, or okay, all the way up to here, it takes 30 minutes to arrive to here. And he said that from A to B, there is a distance of 450 feet. And he said that the V along this is 3 feet per second. So far, so good. So how much time does it take the water to travel, okay, from here to here? So the time is equal to 450 feet divided by 3 feet per second. So this will give you 150 seconds, which is equivalent to 2.5 minutes. Now, what is the time of concentration that should be used for BC, for the design of this BC here, starting here? So what time of concentration? So the time of concentration for the pipe BC is going to be the time of concentration of the largest. Always we'll look for the largest because the water travel from the farthest point. The word farthest point is very important. I needed to remember that, farthest point. So from here to here, I have 30 minutes, which is the controlling one. 10 minutes will not control 20, 30 will control. In addition, from here to here, I have 2.5 minutes. So in this case, the total here is 30 minutes plus 2.5 minutes is equal 32.5 minutes. And this is how we come up with this. Make sense? Okay, good. Good. I'm glad that I was able to grab the question before I say enjoy your lunch. Okay, so right now, okay, so we are going to meet after 1 hour from now, almost 1 hour. Oops, sorry. And enjoy your lunch. Try to make your lunch as healthy and as as good. Okay, you are very welcome, my friend. Let us break here 1 hour again, and bye-bye.